Good afternoon, everyone, and welcome to our Bible talk. This afternoon, Mr. James Thorpe from the Christadelphians in Nottingham will be speaking to us on the subject of the beautiful science of creation. But first, as this is a Bible talk, we're going to start with a short word of prayer to God. So if you just please stand with me, and we'll have that prayer now. Lord God, we thank you for this time that we have to come together to think about your amazing creation, to open your book, the Bible, and to learn from your word. Help us to understand what it has to say and to learn from you. And please be with James as he speaks to us and with us as we listen and learn about you. We offer this prayer now through your Son, the Lord Jesus Christ. Amen. So if you want to listen to this talk in Farsi, there's some QR codes on the end of your row. Just scan them with your phone and you should be able to get to that link. James hasn't asked for an introductory reading, so I'll just hand straight over to him for his talk on the beautiful science of creation.
Perfect. Thank you very much, Joe. Good afternoon, everyone. Hope you're all doing well. This afternoon, we're going to think about the beautiful science of creation. So what do we mean by this? Well, for me, one of the key reasons that I believe in God comes from looking at his wonderful creation. Its stunning beauty, yes, but also how the more you explore its intricate inner workings, the more I find that its incredible elegance screams out that it was designed by a wonderful creator. Now, for a little background on myself, I am a scientist by profession. I'm a physicist. And I therefore greatly enjoy physics. And this is going to be quite a technical physics talk because I want to share with you some of the wonderful things that I've seen in my time studying physics that to me speak of the creation around us and how it is being made by God. And now I'm not the only person who throughout history has been inspired by creation. Throughout the centuries, innumerable people have been inspired by creation and come to the conclusion that it must be the handiwork of God. And this includes many scientists. A good example of this is the great physicist James Clerk Maxwell, who thought that it was essentially essential to be a believer in God to be a scientist at all. Because otherwise, why would you expect to see anything sensible or coherent or logical about the universe that you study? If everything was random and came about by pure chance, it would have no reason to be logical and there'd be no point in studying it. However, I'm getting ahead of myself a bit. So the aim of this talk really is for me to show you how wonderfully elegant all of the fundamental workings of the universe are, or at least some of them. We don't have time for all of them. And how this strongly suggests that the universe is not something that randomly popped into existence, but rather something that was created by the most ingenious designer imaginable, that being God. And so here is a breakdown of how we're going to do it. Here's some pretty pictures of some things you might see in creation, although I suppose in at least one of those cases, if you saw it, it might not be good for your immediate health, but there we go. The plan is that firstly, we're going to have a short warm-up exercise. I'm going to present to you two paradigms, two sorts of things that are random and things that have been designed or things that have been deliberately set up the way that they are. And we're going to consider them, and we're going to consider whether we think something is designed or whether we think something is random. And we're going to think about what makes us conclude which one of those it is. How do we determine if something is designed or something is random? And then once we've warmed up, we're going to plow on into the wonderful world of physics. And we're going to look at how the universe is incredibly well set up or well balanced. And we're going to think of three examples in this. We're going to think with three examples that will show that the universe is perfectly well suited for us to live in it. So we're going to think about fundamental universal law. We're going to think about proton-electron charge balance, and we're going to think about the strengths of the fundamental forces. Now, there may be some strange sounding and unfamiliar words in there, but you are all an intelligent bunch, and I have every confidence in your ability to pick things up as we go along very quickly, and you'll soon appreciate what these all mean. So that's good. And then once we've looked at those three examples, we'll sort of round things up, make some conclusions, and then probably have a cup of tea or coffee or lie down in a quiet, dark room, depending on on our various thoughts. So, on then to our warm-up exercise. What you can see now on the screen or in front of you is a selection of what can very, very loosely or generously be described as collections of rocks. Now, some of these, you would look at them and you would say, yeah, that looks pretty random to me. Some of them, you'd look at them and you'd say, yeah, that's man-made. That's been made, designed with purpose. And I want you to look at each of these pictures here and think to yourself, what category would you put them in? And think about what made you decide which category you put them into. What made you think whether something was random and what made you think whether something was deliberate? So let's quickly go through them all. Top left there, we have the Bridgewater Hall, or just outside the Bridgewater Hall, which hopefully is familiar to many of you. It's a giant sort of pebble-looking thing. Immediately underneath that, so middle left, it is a pile of rocks on top of a Welsh mountain, Glynavach, for those who are interested. Then below that is a stack of pebbles on a beach somewhere. Going into the bottom right, so moving across, we've got the Giant's Causeway in Northern Ireland. Then above that, so top right, we have a dry stone wall, so another pile of rocks on another mountain, different Welsh mountain, Trevan this time. In the sort of what we could generously call middle, I suppose, is what's called the Antikythera mechanism. And then finally, top center is a laptop, which really does push the limits of what we can call a collection of rocks, but there we go. Now, some of these are a lot easier than others. Some of these are easier to define as to whether they are random or whether they are deliberate or not. Very, very few people believe that their laptop is just a remarkable product of time and chance that happens to have fallen together and just so happens to work perfectly. On the other hand, some things are much more difficult. We have three things on the screen that can be described as collections of rocks in the sort of least generous term. That's what they are. So middle left, for example, that's a pile of rocks. Most people would look at that and say, yeah, that looks like a random pile of rocks. But then the pebbles on the beach beneath that, well, is that random or is that deliberate? What makes you think that that pile of rocks maybe is deliberate, but the pile of rocks above it isn't deliberate? What makes you think that? And how does that compare to top right? When it comes to it, the two pictures of rocks on mountains look on face value kind of similar. But then when you look a bit closer, you think, well, maybe that dry stone wall, that looks like it has a purpose. That looks like there's some order to it that you can't see in the pile of rocks on the other side, in the middle left. And then we've got those other two in the other diagonal corners, top left and bottom right. There we've got examples of something that looks kind of natural but probably isn't, and something that looks kind of not that natural but probably is. So the pebble outside of the Bridgewater Hall, that if it was on a beach and you had no concept of scale, you'd probably just think that's a pebble. But its location and various other things to do with its size give away that maybe it's not random. On the other hand, the Giant's Causeway, that looks quite structured and ordered, but actually we could probably say it's not random. Or no, it is random. It's not been deliberately man-made. Then there's the Antikythera mechanism in the middle. Now, I might be wrong, but I suspect that no one out of all of us in this room would be able to say what it does or what it was originally meant to do. You probably can't discern its purpose, but I bet that everyone thinks it was designed for something, even if you don't know what that purpose was. So there we've got some thoughts rattling around our minds now about how we decide whether something was designed or whether something is random. And with these things in our minds, we're now in a position to go on and think about the universe and think about physics. So we're going to think about the balanced universe and how the universe itself is perfectly set up for life to exist within it, or generally just for life to exist at all. And what we have here is the Goldilocks principle. It's the idea that there are some things in life that have to be just right. If they are too hot, that's not okay. That's a bad thing. But if you keep going colder and colder, eventually you get too cold, and that's also a bad thing. There's this perfect spot in the middle, this sweet spot, this Goldilocks zone, where things are just right. The porridge that is not too hot, not too cold, it's just right. The chair that's not too hard, not too soft, it's just right. The bed that's not too big, not too small, is that bed? The one that's just right. You get the idea. And throughout nature, we see lots of examples of things that have to be just right and indeed are just right. Let me demonstrate this with a very simple example. One we're not going to develop too much, but consider the Earth's location relative to the sun. Where we are is lovely. It's not too hot, it's not too cold, it's just right. If we were closer to the sun, then it would be too hot and we couldn't have life. But at the same time, if we were further away, then again, it would be too cold and you couldn't have life. There's a certain acceptance window that I sort of highlighted there in green. That's diagrammatically where we can be. We have to be within a certain Goldilocks zone that is not too hot, it's not too cold. Now, we could think about how big that zone is, but we don't really want to dwell on that because it's quite big, to be honest. What I instead want to highlight now is the fact that we stay within that zone at all times. How often do we consider that? How often do we think about the fact that we are always in this nice Goldilocks zone? It's not too hot and it's not too cold. It's something that happens because we have a nice stable orbit. So this is a picture of the Earth going around the sun that is in no way to scale. But how often do we think about the fact that distance from the Earth to the sun stays pretty constant? Imagine trying to live on a planet which sometimes was a lot closer to its star, so it was an awful lot hotter, and sometimes was a lot further away from its star, so it suddenly went a lot colder. It would be impossible, right? It would be impossible, extremely challenging for life to live on such a planet. So why do we have this nice, stable orbit? What determines this? And the answer is gravity. We all know about gravity to one extent or another. And if I drop an object, then it falls down, gravity. But in a more general sense, what gravity is any two objects with mass will attract each other by gravity. So that's the force that's responsible for the Earth orbiting the sun so nicely. The Earth has mass, the sun has mass, so they attract each other together. The Earth has momentum, which stops it from crashing directly into the sun, so that it goes in a nice orbit. And it's kind of like swinging a bucket around your head on a string, which we all do all the time. The string is pulling the bucket in, but it's got momentum, so it's going away from you, and that makes it not crash into your head, even though it's being pulled in. And gravity can be described with an equation, specifically this equation. This is the force of gravity. It's the product of the two masses divided by the square of the distance between them, times by a gravitational constant. So F is the force, is equal to m1, the mass of one object, times by m2, that's the mass of the other object. There's a g at the start, so that's the gravitational constant. And it's all over r squared, the square of the distance between them. Now, if you have an equation that has something divided by r squared, that's what's called an inverse square law. So if objects are twice as far away, then the force between them is 1/4 of the strength, forming 2 squared. Now, this is very, very important. This is the important part. If this equation was anything other than r squared, if it was r cubed, if it was sine r, if it was e to the r squared, then you wouldn't have stable orbits. What would happen is the Earth would be pulled into the sun and crash straight into it, or it would fly off into space where it'd be too cold, or it'd probably do one then the other if orbits were completely chaotic. In fact, if this force of gravity wasn't described by an inverse square law, then there wouldn't be stable orbits anywhere in the universe, and the whole universe would be an absolute mess. Now, just stop for a moment and think about this. For one thing, how remarkable is it at all that the universe has laws that govern how everything acts? In and of itself, that is contraindicative to the idea that the universe spontaneously came into existence. It seems strange to suggest that the universe just popped into existence and has laws that govern how literally everything within it operate. To me, it seems much more prudent to assume that something allocated those rules that govern the universe. But that aside, our consideration must also be on how there are an infinite possible number of laws of gravity you could have. That could be r squared, as it is. It could be r to the 3, r to the 4, r to the 5, r to the 6. You get where I'm going with that. You have an infinite possible number of options of what the force of gravity could be described by. And if any of those were the case other than the one we have, you wouldn't have life. We just happen to have that one equation out of an infinite selection that allows life to exist in the universe, which I find quite remarkable. Now, with that in mind, we're going to shift gears now in quite a dramatic fashion, and we're going to go from the very, very big and solar system stars and planets down to the very, very, very small. So we're going to go down into thinking about atoms. So there's an atom for you. Atoms make up everything in the universe. Everything from cars to stars to armadillo-shaped lead paperweights are made up of atoms. And possibly what you see on the screen before you is what you might think of when you think of the word atom. It's not a bad description. You have a blob in the middle. That's called the nucleus. And then it's got some smaller blobs whizzing around it, kind of like planets around a star, which is kind of elegant in a way. And those things that are whizzing around, they're called electrons. So we've got nucleus in the middle, electrons orbiting the nucleus. Here's a slightly more detailed depiction of an atom. So we've sort of changed it so that we can now see that the nucleus itself is made up of further things. It's made up of what are called positively charged protons and neutrons, which are neutrally charged. And this is not in any way to scale, far from it. And the electrons, as we discussed, they are negatively charged and they orbit around the nucleus. Now, an atom is defined, what atom that is defined by the number of protons present in the nucleus, which is reflected in the number of electrons orbiting said nucleus. So in this case, it's often easier to count the electrons. So we can see it's got 8 electrons. You can't see it quite as clearly, but let me show you it has 8 protons. And that means that this is a depiction of an oxygen atom. And as a fun fact, oxygen makes up most of your body by mass. However, this is what makes up most of the universe. This is a hydrogen atom. It's the simplest atom you could get. It's just one single proton with a positive charge and one single electron with a negative charge orbiting it. Now, if we think back to gravity for a moment, we said that any two objects with mass would attract each other. So we had a property, mass, and that was related to a force experienced, gravity. Now we're going to add another property into our considerations. We've already mentioned the word a few times, and that is charge. So mass relates to charge. So mass relates to gravity. That's what we just said. Charge relates to a different force called the electromagnetic or the electrostatic force. And when it comes to charge, things are a little bit more complicated than with gravity. So in gravity, everything attracts everything else. Anything with mass pulls anything else with mass together. It's one directional. Whereas with charge, things are a little different. Two opposite charges will attract each other. A positive and a negative, they will attract each other. Two of the same charge will repel each other. So positive and a positive, they'll push each other apart. Negative, negative will push each other apart. Positive, negative, they attract. It sounds like a bit of a complicated concept, but if you consider, if you've ever had two bar magnets with a North Pole and a South Pole, then you'll appreciate this. So if you try and push together two North Poles, they'll push apart. It's really hard to push them together. You can't see the force, but it does it. Magnets. Whereas North and South, they click together straight away, no problem. So where am I going with all this? What's my point here? Well, I just mentioned that hydrogen is the most common element in the universe. The sun is mostly hydrogen. That's what it's made of primarily. Quite a lot of helium as well, but mostly hydrogen. Most stars are made of purely hydrogen or mostly hydrogen. You also get some things in the universe like this. This is a nebula. Specifically, it's a section of the Tarantula Nebula. And what you're looking at here on the screen is an enormous cloud of hydrogen with admittedly a few other elements chucked in there, but it's primarily hydrogen. And when I say it's enormous, I mean vastly, unimaginably huge. It spans the whole nebula over 1,800 light years, which is 10 to the 16 miles. So that's one with 16 zeros after it, miles across. It takes light nearly 2,000 years to get from one side to the other, which hurts my brain when I start to think about it too much. And the reason I'm showing you this is for two reasons. One is because it's very, very beautiful, which I thought I should mention, because this is a talk entitled The Beautiful Science of Creation. So it is very, very beautiful. It's an enormous piece of artwork, effectively, cosmic artwork, written in the sky, written across the heavens, as it were. But the other thing about it that's very interesting, because there's lots of things that are interesting, but the one I want to point out is this kind of nebula can be thought of as a star factory. This is where stars are made. And the process of which stars are made is that you get a very, very huge cloud of hydrogen gas. This is bigger than you need, but within it is lots of smaller clouds of hydrogen gas. And what happens is the hydrogen gas, these hydrogen atoms within this cloud of gas, they all have mass. And as we've just discussed, that means that they're all going to attract each other. So they're all going to pull each other together. And as they pull each other together, they clump together. And as they form clumps, that pulls in more hydrogen, and that makes the clump bigger. And it gets bigger and bigger and bigger, and they're all pushing in on each other. It's a big pile-on of hydrogen. And at the center of that, they're rubbing together, these hydrogen atoms. And it starts to get hotter and hotter, and the pressure gets greater and greater as more and more hydrogen keeps piling in. And eventually, the heat from them rubbing together, from that friction and from the pressure pushing down on them, will become sufficiently high that nuclear fusion can occur. And when that happens, a star is born, and it starts to burn super, super hot, super, super bright, and that's a star. Lovely. Just pause for a second, because there's a few components out of that I want to highlight. So firstly, stars form when hydrogen is represented with a H, is attracted by gravity together, so it clumps together. Secondly, so what is hydrogen? Hydrogen is one proton and one electron. That's what makes up a hydrogen atom. And these atoms are being pulled together to form stars. And thirdly, most importantly from the other 2 points, hydrogen atoms have no overall charge. Okay, now what's this? What do we mean by this? Well, protons are positively charged, electrons are negatively charged, and it just so happens they have exactly the same charge, just in the opposite direction. So a proton has a value of +1, an electron has a value of -1. So when you take +1 and add -1 to it, you get 0. Make sense? So overall, the hydrogen atoms have no charge in and of themselves. Why is that important? Well, it's important because that means that there's no charge, there's only mass in this big cloud of hydrogen. So the only force that's acting on it is gravity, and that's pulling it all together, which is very, very handy, because then you get stars, and you need stars for life. But what if that wasn't the case? What if the hydrogen atom had a slight charge? What if that, so your proton and your electron, they're not perfectly balanced, they're slightly off, and that means that hydrogen atoms have a slight charge. So let's say the proton is slightly more positive than the electron is negative. Then every single hydrogen atom has a slight positive charge. And if there's a slight positive charge, then that means that all of these atoms are going to have a force acting each other from the electromagnetic force, as well as from gravity. And because they're all going to have the same charge, they're all going to be slightly positive, that means that they're all going to be pushing each other apart. They're all going to be repelling each other. And that's then kind of tricky, because if we've got two forces, gravity pulling them together so they can form a star, and electromagnetism pushing them apart so they can't form a star, what's going to happen? Eventually, there's a certain threshold of charge where if a hydrogen atom has that much charge, then it's going to push away the hydrogen atoms, and you can't form stars at all, and you can't have life. And what we want to do now is I want us to work out how much charge we can get away with. So brace yourself, because we are going to do some maths here. Often with a talk like this, I would just tell you what the answer is and tell you how much charge you need. But on this occasion, I think it would be beneficial for us to work it through and calculate it specifically, so that you can see that I'm not just plucking numbers out of the air. Now, I realize this is going to be a little bit complicated. It's going to be a bit maths based. So just bear with me on this, because I think it's really important to show that these kind of things are real. These are real phenomena, real calculations we can do. It's not pseudoscience. It's not just being plucked out of the air. So the question we're trying to answer is, how much charge can we get away with? At what point are atoms too charged to draw together to form stars? So let's work through some maths. So we begin with gravity, where we did before. So that's an equation we had earlier on. Fg, we've put a g next to the F to show that that's the force due to gravity, is equal to gm1 m2 over r squared. That's what we had before. In this case, we have two hydrogen atoms, so m1 is the same as m2. They're both hydrogen atoms, so we can just call them m and call it m squared. So gm squared over r squared. So far, so good. Now, as it happens, the electromagnetic force has a very, very similar equation that describes it. It looks like this. So Fe, force due to the electromagnetic force, is equal to 1 over, and then there's this strange thing that starts 4 pi, that weird E is an epsilon naught, so 1 over 4 pi epsilon naught. Epsilon naught has the very fancy sounding name of the permittivity of free space, but really you can just think of that initial thing as being the electromagnetic constant, like we had a gravity constant before. What those constants do is they take the other values and they turn it into a real world number. Then we've got Q. So what Q is representing charge in the same way that M represents mass. So we've got two charges, Q1, Q2. Again, we have the same situation. We're thinking of two hydrogen atoms where we've said that they're slightly charged, but they have the same charge because this charge is coming from the fundamental makeup of their proton and their electron, which means that that comes to Q squared. So two forces, Fg equals gm squared over r squared, Fe equals q squared over 4 pi epsilon naught r squared. And what we're saying is that the electromagnetism, Fe, is pushing them apart, it's repulsive. Fg is attractive, it's pulling them together. We want them to pull together, we want to make a star. So the limit that we have is that the electromagnetic force pushing them apart has to be smaller than the gravitational force that's pulling them together. So Fe has to be smaller than Fg. Substituting that in gives q squared over 4 pi epsilon naught r squared has to be smaller than gm squared over r squared. We're getting there now because we can start to rearrange this. There's an r squared on both sides, so we can cancel that out. Well, there's a 1 over r squared on both sides. We can cancel that out. We can divide or times through. We can square root it, rearrange it into a more easy to represent form because, as I repeat, what we're looking for is we're looking for what charge can we get away with? What's the smallest charge we can have on an atom where it stops us from forming stars? Q has to be less than the square root of 4 pi epsilon naught gm squared. Lovely. This is lovely because we know what the gravitational and electromagnetic constants are, and we know what the mass of a hydrogen atom is, which means that we can just plug in a whole load of numbers like so. And we get Q, the absolute value, absolute charge of the hydrogen atom has to be smaller than the square root of 4 pi times by 8.85 times 10 to the minus 12 times by 6.67 times by 10 to the minus 11 times by brackets 1.67 times 10 to the minus 27 squared. Okay, quite a mouthful, but it's all a lot of numbers, so we can just calculate it. And this is what we get. Q, which I'm going to remind you, is the charge of a proton plus the charge of an electron. The absolute value of that has to be smaller than 1.424 times 10 to the minus 36 C. C is coulombs. So coulombs is just the unit of charge in the same way that kilograms kg is the unit of mass. So the absolute value of atomic charge for a hydrogen atom has to be less than that for stars to form. Now we're going to do something slightly strange because I'm more interested in the balance between the proton and the electron than I am the absolute value. So I'm going to divide through by the charge of an electron. We know what the charge of an electron is. The charge of an electron is minus 1.6 times 10 to the minus 19 coulombs, which means that the ratio between the absolute total charge of the atom and the charge of the electron has to be approximately 1 times 10 to the minus 17. Okay, that last step might seem a bit odd. I appreciate I might have lost a few of you there. But what we've done is we've said, okay, we know what charge is unacceptable. So if we say that an electron has this much charge, how much leeway do we have in the proton? What's the give we have in a proton? And the answer is it has to be accurate to 1 in 10 to the 17. That's what that last bit says. So that's what we're saying here. We're saying that the balance between the proton and the electron charge has to be accurate to 1 part in 10 to the 17 for stars to form. If those two aren't balanced to that level of accuracy, you can't have stars, you can't have life. So what does 10 to the 17 mean? Well, that's it written out. It's a 1 with 17 zeros after it, which is a very, very big number. It would be called 100 quadrillion, if you were to sort of put a name to it. It's big. If you're not balanced to 1 part in this, then you can't have stars. Now, I'm still struggling to work out how balanced that is. It's not very obvious as a number. I can see it's a big number, but it's hard to see how big a number that is. So I tried to come up with a way of illustrating this, a way of showing you just how well balanced this is. And the way I've opted to do this is to put it on a scale. So let's say we're making a universe. We're making our own universe. And we have this scale, and this scale sets the charges of the proton and the electron. Now, we've already set our electron charge, you can see there, and we've made it negative. 0 is in the middle, as you can see, and then we're going positive beyond that. So we're trying to balance this. It's like a seesaw. It's like a set of weighing scales. We're trying to make it perfectly balanced, and it has to be balanced with an accuracy of 1 part in 10 to the 17. So how well balanced is that? Okay, the charge of the proton has to be approximately on the opposite side, approximately the right distance away. But are either of those two other options, are they accurate to 1 part in 10 to the 17? Well, it doesn't really look it to me, but how can we say? How can we define it? The problem I've got is there isn't really enough space on the screen in front of you to properly demonstrate how well balanced 1 part in 10 to the 17 is. Earlier on, when we had that picture of the sun and the 3 Earths, and I put one of them in a band of green and said that was the acceptance window. Imagine we were doing the same here. Imagine we have a band that is green, and that says where we can put the charge of a proton on that line. The problem we have is you can't visualize it on the screen. It's too small. It's smaller than a pixel on the screen, which is a problem. So what we'd have to do is we'd have to increase the size of our scale so that we can visualize it. So let's sort of say that we're changing the size of our scale and we're making it this big. So we're making our scale where we're setting the charge of the proton and the charge of the electron the size of Earth's orbit around the sun. So the center of the sun is 0, and the charge of the electron, we've already set that is the distance from the Earth to the sun. And on the other side, we need to put the charge of the proton, and again, it needs to be the distance from the Earth to the sun. But how precisely does it have to be that distance? Well, with a line that is stretching from the diameter of Earth's orbit around the sun, the green acceptance window that we're trying to represent here is 1,000th of a millimeter wide. You needed a microscope to be able to see that kind of level of precision. That's how precise the charge of the electron and the charge of the proton have to be. They have to be balanced to within 1,000th of a millimeter on a scale stretching across the orbit of the Earth around the sun. That's how unbelievably well balanced the charges of the proton and the electron are. If you tweak that, if you nudge that just by 1,000th of a millimeter, and boom, you have no stars, no life, no boring science lectures by James on a Sunday afternoon, which shows that you can't win everything. And just for an extra little thought, for those of you who know a little bit more physics, the mechanism from where the charge of the electron and the charge of the proton come from is slightly different, because an electron is a fundamental particle. It can't get divided any smaller. The charge of the proton actually comes from some subatomic particles, which means it's even more remarkable that it's balanced, but we will not think about that. Now, hang on for a moment. If your mind works in a very, very strange way, then a question may now be floating around in it, which maybe I can stir up with this picture from earlier on. This is an atom. It's a slightly more complicated atom than a hydrogen atom. This is an oxygen atom, we said, and it has 8 protons in the nucleus, 8 positively charged protons. Now, we were just thinking about how 2 objects with the same charge push each other apart, and it didn't seem to take much charge to cause a very significant force that sort of stopped us from forming stars. And that would be because the electromagnetic force is much, much stronger than gravity. I can demonstrate that very easily if I take my glasses case here and hold it up. The atoms at the bottom of my glasses case are being pulled down by gravity. There's a whole planet trying to pull the atoms at the bottom of this case downwards. So why doesn't my glasses case stretch and all the atoms fall off the bottom? Due to gravity. And the answer is that the electromagnetic force between all the atoms in the glasses case are pulling them back up again. And it's much, much stronger. So even though there's only, not as many atoms in this as there is a planet beneath me, it's still strong enough to hold this together nice and robustly, despite the fact that an entire planet is using gravity to pull it down. Hopefully that makes sense as an idea of how strong electromagnetism is relative to gravity. So if gravity is weak and electromagnetism is very, very strong, then we have a problem, which is, why isn't this nucleus flying apart? It's got lots of protons. The protons are all positively charged. The neutrons are neutrally charged. They're not contributing in any way to the electromagnetic force. They're not pulling anything in. So why is it sticking together? And if you're thinking it's anything to do with the electrons, even if we removed all the electrons, it would still stay intact. The nucleus would stay intact. It's intriguing, isn't it? And the answer as to why this nucleus isn't flying apart comes from another force that I haven't mentioned yet. You see, the universe has more than just gravity and the electromagnetic forces acting within it. And there are, in fact, 4 fundamental forces that describe our universe. The whole universe is governed by just 4 forces, and these 4 forces pretty much describe absolutely everything you can see in the universe. So what are they? Well, we've already met gravity and the electromagnetic force. They are now our friends. But there are 2 more, which are called the strong force, or the strong interaction, or the strong nuclear force, and the weak interaction, or the weak nuclear force. Now, the weak force, the weak interaction, is mostly just called the weak interaction because it's a bit weird. It doesn't work like a force like the other ones do. It's a bit of an odd one. It relates to sort of nuclear reactions, and we're not really going to dwell on it. But we are going to think about the strong interaction, or the strong force, or the strong nuclear force. You get absolutely no points for guessing what the defining feature of the strong force is. It's very strong, very, very strong. So strong that even though all the protons in the middle of the nucleus are pushing each other apart due to electromagnetism, the strong force holds them together. That's why our nucleus doesn't fly apart. And the neutrons do contribute to the strong force, which is why they're present as well, to hold it all together. Now, I quite like putting things on scales, so let's put the strengths of all of these forces on some scales to see how they compare, like a really bad game of top trumps. So here we are, the 4 fundamental forces laid out nice and neatly on a scale. So what we've got here is we've got at the strongest end at the far right, we have the strong force, or the strong interaction. And it's so strong that we're setting that as our reference point, so everything else is being defined as how strong is it compared to the strong force, or the strong interaction. So it has a strength of 1 on this scale, or 10 to the 0, which is 1. Now notice this scale is not a linear scale, it's logarithmic. So each tick you go along it is getting 10 times smaller, not just 10 smaller, 10 times smaller. And you'll notice there that electromagnetism is 2 ticks along. So it's got a strength of 10 to the minus 2. It's 100 times smaller than the strong interaction. So quite weak, 1% of the strength of the strong force. That's very weak. The weak interaction is even weaker. That is 10 times 10 times minus 10 times the strength. That was a really cumbersome way of saying 10 billion times smaller. That's an easy way of saying it. So 10 billion times smaller than the strong interaction makes it very weak. However, it's still an awful lot stronger due to gravity. So someone messed up naming that one because gravity is sitting right at the far left at 10 to the minus 40. So it's 10 to the 40 weaker than the strong interaction, or the strong interaction is 10 to the 40 times stronger than gravity. Now that is an enormous difference. Hopefully we're starting to get the feeling of how big numbers work. So going the other way, how's gravity compared to the strong interaction? The strong interaction is 10 to the 40 times bigger. 10 to the 40 is that. It's 1 with 40 zeros after it. Before we were thinking about 10 to the 17, and that seemed like a big number. This is a staggeringly big number. But why do we care? Why am I going on about this? Well, the reason we care is that you need the strengths of the strong force and gravity to be balanced by this amount, 1 in 10 to the 40. If you were different from that, then you wouldn't be able to have stars. So let's put that on a scale to work out how big that is, because again, it's a number that's very, very difficult to sort of wrap your head around. So what we have here is a scale like we had with proton and electron charges. This time it's saying how strong are the strong force and the strength of gravity. So the strong force, that's on the far right. So we're saying if you put gravity on the far right of the scale, it will be equally as strong as the strong force. On the far left is 0. So if it's there, then gravity has absolutely no strength at all. Now, it can't be 0. It's going to be next to 0, but it can't be 0 because this is a balance, a Goldilocks situation, too small, and those atoms won't pull together to form a star. So it's got to be strong enough to actually pull them in. If gravity is too strong, then it pulls everything in too fast, and that causes the stars to burn too quickly, and again, you have no life. So again, we have an acceptance window. We have a Goldilocks zone, which is just right. It's not too weak so that we don't form stars at all. It's not too strong so that stars immediately burn out. It's just right. And again, we want to highlight it in bright green, but again, the screen is too small to show the precision of 1 in 10 to the 40. So again, we need to increase our scale. We need to really stretch it out and zoom out a lot so that we can try and see this. So this is what we had before. Before, when we were thinking about the charge balance between protons and electrons, we said it had to be balanced to 1,000th of a millimeter on a scale reaching across the orbit of the Earth. However, on this occasion, 10 to the 40 requires us to have a much, much, much bigger scale. So we need to really zoom out. And what that hopefully represents in a way is the entire universe. So this scale now stretches across the width of the entire universe. And we have a green acceptance region, a green acceptance band on this scale stretching across the entire universe. So how big is this acceptance window now? How big is this Goldilocks zone on a scale stretching across the entire universe? Is it light years across, miles across, meters across, millimeters across? It'd be smaller than an atom. That's how incredibly well balanced the strength of gravity and the strength of the strong force are. If you were trying to put gravity on that scale, a scale that stretches across the entire universe, you would have to be accurate to within the width of an atom. If you knock it by an atom's width, then you've messed up the entire universe and it's not going to have life. It's not even going to have stars. And that is what I would call extremely well balanced. That is what I call a beautiful design, not something that could come about by chance. And there is, in fact, in this, a further beautiful thing, a lesson hidden for us in the science of creation, a spiritual lesson. This is how much God cares. God cares on the scale of a single atom across the span of the entire universe. If he hadn't put that much precision into his creation, it wouldn't work at all. There'd be no life. There'd be nowhere for life to exist. So if you're ever thinking, well, the world is so big, the universe is so big, how could God possibly care about something so small as me? Remember this scale. God cares about something smaller than an atom on a universal scale. He cares about each and every one of us, that's for sure. Now, with this, we're going to round up our thoughts on physics. But let me first point out that there are various other things that we could have considered. We could have thought about the range of fundamental forces. You might now probably be wondering, well, if the strong force is so strong, then how come all matter in the universe isn't in a dense tight blob in the middle being held together by the strong nuclear force? And the answer is that the nuclear force works on a very, very short range. It only really works across the nucleus of an atom, hence why it's called the strong nuclear force. By comparison, gravity, being extremely, extremely weak, works over a very, very long range, an infinite range, potentially. And that means that it can operate over the scale of stars and planets and nebulae and so on, whilst the strong force is limited to just the nucleus of an atom. And again, these ranges of these forces have to be incredibly well balanced. So the strength and the range of these forces has to be balanced. We looked at the strength, we could have looked at the range. Again, we looked at charges and we thought about the fundamental charges of particles. But we could have thought about the mass of fundamental particles. We could have thought about how the mass of the proton and the neutron has to be perfectly balanced for nuclear fusion to happen. We could have thought about all sorts of other things, but we didn't really have time, and it would have been complicated. So yeah, there are all sorts of things we can see in the fundamental makeup of the universe that would lead us to the conclusion that it must have been created. That's what I'm putting to you. Now, you may be wondering, well, James, if the universe is so incredibly well balanced that it seems dead certain that it was created, then why do some people not believe this? You know, there must be a reason why other people have concluded that this isn't a thing of design. And this is the most common rebuttal you'll hear to the idea that the universe is incredibly well balanced. And it's the idea of a multiverse. It's the idea that we're not living in just one universe, but in multiple universes. Maybe there's an infinite number of universes out there, or an innumerable amount, possibly infinite. And what happens is in each of these universes, conditions are slightly different. So the fundamental laws of nature are just ever so slightly different. So in one of them, gravity operates in an inverse cube law. In one of them, gravity is 10 to the 20 times weaker than the strong force rather than 10 to the 40. In one of them, the proton and the electron aren't balanced at all. And in all of those other universes, there's no life. But we just happen to be in the one that does have life. And that's not so much a coincidence, it's because we're in the one that has life so we can see it, which is why we see the one that we're in. And that's sort of that's known as the strong anthropic principle. Now, you'll hear a lot of quite big atheists, quite strong scientists talking about this idea, the idea of multiple universes, as a way of explaining why these incredibly balanced forces that we see to them don't necessarily suggest that there is a creator. The thing is, there's absolutely zero evidence to suggest that there are multiple universes. But by definition, they cannot interact with each other. That's absolutely impossible. Otherwise, they would have already. So not only can they never interact with each other, they never will. Which means that not only is there no evidence now, there never will be any evidence to suggest that there are multiple universes. It's something that requires absolute blind faith to say that it's true. The only reason if you're saying the only reason the universe looks designed is because it is one of an infinite number of universes that are all slightly different, that is a sentence of pure faith, not based on any observation, not based on any science whatsoever. And so I shall leave it there and we will wrap things up. So this afternoon, we've been thinking about how fundamental laws of nature are extremely well balanced, extremely well suited for life. We thought about two specific examples of this in the balance of the charges of the proton and electron and the relative strengths in the four forces. And at the start, we also thought about fundamental universal law with the law of gravity itself. And at the start, we thought about, in our warm-up exercise, how we decide whether something is random or not, how we decide whether something is random or deliberately designed, whether it has purpose, and how perhaps balance helps us to consider this. I'm jogging your memory of that now with another picture of a pile of stones. Is that one random? How well balanced is something before you say that it's no longer random? So if you've got one stone on top of another stone, that's probably random. A stone could fall on another stone. That's fine. You might even have a pile of 3 stones or even 4 stones and think, yeah, that's probably fine. When you're as tall as that one there on the screen, you're probably thinking someone had to balance that. That looks too well balanced to be coincidental. What if it was a pile that was, 10 meters high, 20 meters high? How well balanced would that be? Would you say that was a coincidence? And the thing is that the fundamental laws of the universe are extremely well balanced, far more so than you can see in that pile of stones there. Far more so than is reasonable to say that this is something that is accidental. This is something that happened purely by chance. And if something doesn't happen by chance, then it has to have had someone designing it, has to have someone giving their intelligent input. In short, it implies the universe has a creator, someone who deliberately set everything up for it, deliberately set up these fundamental laws that govern everything. And that creator is God. And that's why I believe in God. Well, that's one of the reasons I believe in God. Now, it's definitely worth pointing out at this point, right at the very end, that this points out that there is a God. This is why I believe that. But once you have accepted that, then you have to start thinking about, well, how do I get to know God? How do I start to understand more about him? And how do I get to find out what his plans are? Is he interested with us? And that's where the Bible comes in. That's where we read his holy word. We read this and we can learn from this about him. That's where things become really important. And there are going to be lots more talks on Sunday evenings or afternoons, I'm sure, that will help to explain more about God now that we have thought about his existence. Thank you.
I'd like to thank James on your behalf for his talk and for explaining the complexity and the perfect balance of nature and God's creation. So thank you, James. If you're interested, we have a website which is sale-christadelphians.net, where we have lots of content, some along the same lines as James's subject tonight. And we also have some literature at the back of the hall on a variety of subjects to do with God and the Bible. I didn't have a look before we started, but I'm pretty sure there is one about science up there. So please feel free to take some along to read alongside your Bible. Some announcements for the week ahead. On Tuesday at Bible class at 8 o'clock, Mr. Samuel Brown from, I think it's Preston, is that right? Yeah, Preston, will be speaking on the subject Psalms, Hymns and Spiritual Songs. And then next Sunday at 2:30 for our Bible hour, Mr. Ed Bamford from here in Sale will be speaking on the subject, Can we ever have a world without war? So thank you for coming. I hope you found the talk interesting and helpful, and we hope to see you again soon, God willing. So would you just please stand with me again, and we'll bring our time together to a close through a prayer. Our Father in heaven, we thank you for this time we've had together. We thank you that we have been able to see the wonder of your creation in more detail. We can see your power and your amazing design all around us and in the grandest and the smallest of things. May we never take anything for granted, but always give you praise for the things that we have. Please bless us now as we go our separate ways, and be with us until we meet again, if it is your will. And most of all, however, we pray for your Son's soon return to set up your wonderful kingdom. It's through him that we offer our prayer. Amen.